All right, good morning. How was the exam? Thumbs up, thumbs down? Eh. All right, we'll see. Yeah, I'm sending the exams today, and they'll probably process that either today or Monday. So expect to get them back middle to late of next week, the scores. And then your actual exam probably the following week. All right? Okay, today we'll finish up the section on Taylor series. And today we're going to look at the Taylor series of a function that you actually encounter this quite often in various applications in engineering and physics. There are many times you need to get some kind of approximation of this. So let's find out the Maclaurin series of this. And as a reminder, that's what we need to do to get our Maclaurin series. We need a bunch of derivatives at 0 and so on. All right, so as usual, we start with the function itself. And let's take the first derivative. And this is pretty easy to differentiate. Just simply the power rule over and over again. Right? Bring the k down, keep the base, reduce power by 1. Do that again to get a second derivative. Third. And now we're seeing a pattern here, right? The exponent reduces by 1 each time we differentiate. And the stuff in front of 1 plus x. There's also a pattern here. The third derivative has k minus 0, minus 1, and minus 2, up to 1 less than the derivative order. So let's generalize that. Looking at the pattern here, the nth derivative would be k times k minus 1, k minus 2, all the way up to 1. Look at the pattern here. What's the last one I would put here? K minus n plus 1, right? So k minus 3 plus 1 gives me k minus 2. K minus 2 plus 1 gives me minus 1. See that pattern? So k minus n plus 1. What about the exponent of 1 plus x? K minus n. Good. Okay? Okay, so that's pretty nice. Let's see what happens at 0 then. We need those things at 0. So that's, of course, just 1. And f prime at 0 is k, right? F double prime at 0 is k times k minus 1. Triple prime, k minus 1, k minus 2. And then finally, generalize that to the nth derivative, this guy right here, k minus 1, k minus 2, all the way up to k minus n plus 1. Okay? Okay, now we got these f, the nth derivative at 0. Let's put the series together and see what it looks like. So 1 plus k, x to the k, according to the formula for the Maclaurin series, is the first one, 1, plus k over 1 factorial x, right? Plus k minus 1 over 2 factorial x squared, plus k minus 1, k minus 2 over 3 factorial x cubed, plus so on. So these things get a little bit longer each time. Let's just scratch it out. You get the idea here. The pattern is pretty easy to see. The next one would be k minus 1, k minus 2, k minus 3 over 4 factorial x to the 4th. Okay? All right, so now let's put this in the summation notation. See how you would put this together in the general form here. Upstairs, depending on the number n, the length of what the expression upstairs changes. In general, it's going to look something like this. Right, all the way up to whatever n you want it to be. And downstairs is pretty easy, n factorial. And then we have x to the n. All right, so that's what it looks like. It looks a little bit interesting because the numerator is different for each n, and the number of numbers you multiply is different for each n. And this thing is going to converge if the absolute value of x is less than 1. And you can verify that by using ratio test to see that. And this is called the binomial series. If you look at binomial series, you'll find out it has lots and lots of applications. And Newton actually tackled this problem before he invented calculus. So today we use calculus to get all these derivatives, and we put it together. It's not terribly difficult. But Newton did this without using calculus. And if you want to look up what he did, it's pages after pages of pretty complicated stuff. This thing is also written this way. So all of this really strange looking fraction here, you can put it compactly in this notation. This is called a binomial coefficient. If you take a course on probability, you'll see this a lot. You'll be calculating binomial coefficient. It's used very, very often in things like probability and statistics. And k, this is the way you read this is k choose n. Okay, so that's the binomial coefficient. All right, so everything on this page will be given to you on the final exam if you need to use something to do with a binomial series. We're not going to make you memorize the formula here, but you need to be able to use it to come up with a series for something we give you. Okay, so let's try this on a couple examples. Let's find a series for the fourth root of 1 minus x. And to make this work, we got to put this in the form of 1 plus x to the k. And of course, this x here could be different. It doesn't have to be x. Just like when you did modification with the geometric series, this x could be something different. So this one here, let's put it in this form. We want 1 plus something. So let's do 1 plus negative x. So this will be my new x in that expression. And then we'll raise that whole thing to what power? Right. Fourth root is 1 over 4. Okay? So here, k is equal to 1 over 4 in the formula that we saw on the last page. And that x in all the expression is really just, it's going to turn into negative x. And when you calculate when you find the binomial series, the first line is the most useful form to deal with. This allows you to put it in a very compact form, but it's not computationally useful. The first one is the computationally useful form. All right, so let's try that. Well, let me write this that way. 1 plus minus x, the whole thing to the 1/4. All right, first one is 1, regardless of what x is. Then we have kx plus k, and x here is negative x, right? And then k minus 1 over 2 factorial x squared right? Get the idea here? All right, so how about next one? What's going to be on the numerator for the next one here? Negative 3/4 and negative, right. We're subtracting 1 each time, yep. And downstairs is 3 factorial negative x cubed Let's go one more, just so we are seeing the pattern here. We're subtracting 4 over 4 each time. So notice the numerator of the numerator increases by 4 each time, right? So next one would be negative 11 over 4, right? Downstairs is 4 factorial, and then negative x to the 4th plus dot, dot, dot. Questions on this? How we got that? Okay, now let's modify this a little bit. You'll see a pattern once I make a little bit of a change to a few things. Nothing to do with 1, we'll leave 1 alone. Negative 1 over 4x. Negative, right? Overall negative. Negative. And upstairs, it's 1 times 3. And downstairs, I have a 4 times 4, 4 squared, times 2 factorial, positive x squared. All right? So I brought the denominator of the numerator down to the proper denominator. We're allowed to do that. And then here we have negative, 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 overall net negative again. Upstairs is 137. And then 4, 4, 4, 4 cubed. 3 factorial. X to the 3rd. Next one, negative, 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 positive, all negative. 1, 3, 7, 11. 7, 11. Huh, look at that. Oh, what am I doing? And then 1, 2, 3, 4. 4 of those 4s. 4 factorial. X to the 4th. You see a pattern here? Yeah? What's the next one then? What do you think next one would be? 15, yep. 1, 3, 7, 11, 15. It goes up, the last one goes up by 4 each time, right? How about downstairs? 4 to the 5th, 5 factorial, x to the 5th. Okay, this pattern actually is quite nice. Now these numbers, when you multiply them together, may not be very pretty, but the pattern is very, very nice. All right, now we're going to put this put back into a summation notation that's simpler and actually explicitly shows this pattern. So as usual, let's mark up the n's we're going to use for these things. Starting with n equal to 0 is always a very nice thing to do. Now when you look at these here, so let's know the pattern here. The last number in numerator. I'm going to start looking at n equal to 2 here, because by inspection here, these two look quite different from all the other ones. So let's leave them out here. Let's find out a pattern that all of the other ones are obeying, and then we'll put it together. So the last number here is 3, 7, 11, 15. Can you guess the next one? 19. And then the corresponding n, 2, 3, 4, 5, and 6. Now we're going to find a way to express those numbers in the top row, each one as a function of n. First, you look at by how much they're going up each time. They're going up by 4 each time. So you're going to do a 4n. Right? Each time you go up by 4. 4 difference, 4, 4. So 4n to start. And then you make sure that these numbers match up. 4 times 2 is 8. 8 is not 3. And 3 times 4 is 12. 12 is not 7. So what do I need to modify this to make sure the numbers? Subtract 5, exactly. So that's how you see the pattern here. Look at by how much they're going up. That's the coefficient of your n. And then you either need to add or subtract something to make sure the numbers on the top row you get the numbers on the top row. Make sense? Okay, now in the summation notation, the first two, like we said earlier, don't look like the rest of them. So we're not going to force them to live in the summation. We found a nice pattern for n equal to 2 and beyond, and that's great. And we'll leave the first two outside. And then start a new summation starting at n is equal to 2 to go to infinity. And now look at the numerator. All of them are going to have 1 times 3 times something. So here's the way we write it. It's 1, 3, 7, 11, 15, so on. And then the very, very last number is 4n minus 5, right? That's why we determined the relationship between the number, the last number in the numerator, and n. And then downstairs we see 4 to the power of n, and then a 2, or rather n factorial. And then we have our x to the n, right? So again, these look a little bit peculiar, but when you write this out, you have to make sure you read the right n. When n is 2, this is what? 3. So this tells you to stop at 3. When n is 2, you do 1 and 3 and you stop. You don't go to 7. This thing tells you where to stop. When n is 3, we get 3 times 12. That's 3 times 4 is 12 minus 5, 7. Tells you to stop at 7. So 1, 3, 7. When 4, you get 11, so you stop at 11. And just like you could reuse your geometric series, we know in the original formulation, x has to be less than 1, the absolute value of x. And now in this example here, our x is negative x. So here we have this condition here. And that's going to give you a radius of convergence of 1. Yep, that's usually what we care about. Question? Right. You're starting at 2, so it's this term right here, right? And then this thing tells you where to stop. You don't. Not every term gets 7. The first one doesn't get 7. So when you put n equal to 2 into here, you get 3. That tells you to stop at 3 and don't go beyond 3. When n is 3, you get 7. That tells you to stop at 7, but don't go beyond 7. So this goes as long as this number is not duplicating these, but you stop at this number no matter what. And you can see that 1 doesn't work, right? 1 gives you a -1. That's not going to work. So we don't start at 1. The negative? Okay, yeah, I missed that. So how do I fix that easily? How about I change the sign to a negative? Would that fix it? That would make everything after that a negative, right? So I could put it into here if I want to. Or I can put it out here, make the whole thing negative. Either way, it would give me the right signs. Other questions? Yeah.
Does 4 behind not play with the radius here? Do the ratio test you want 4?
It actually wouldn't. If you carry this out, well, first of all, if we use this formulation here, we know this is going to converge if this is strictly less than 1. And we did a similar stuff with geometric series thing. It's whatever x that you're changing here. So here our x is negative x. That 4 goes into k. Notice that the convergence of this thing has nothing to do with k. And the consequence of that 4 came from the k business here. So that k part doesn't factor into the convergence. Even though, like you said, when you look at it and if you apply the ratio test, it looks like it should matter, but it doesn't actually. Yeah.
Why do you have the absolute value of negative x? Like negative x never shows up in the final equation.
But this is my x when I use the formula 1 plus x to the k, right? I have 1 plus minus x to the 1/4. So this thing converges if that x is strictly less than 1, the absolute value. Here I'm using a different x, using the consequence of that formula. So here the convergence is that.
So the convergence is not based on the resulting sum, it's based on the original equation, the original expression.
If you actually use the ratio test, you'll get the same result. And we're skipping that step because we're taking advantage of what we already know about the convergence of that binomial series. All right? It's the same thing we did with the ratio, not the geometric series thing. When we change x, we take advantage of that fact and say that new x has to obey the geometric series rules. All right? All right, let's do a couple more. So this time, we're going to make things a little bit complicated. Yeah, a little bit. Okay, so we got 5 over 6 plus x to the third. And once again, we want everything to look like 1 plus something, right? So this is 5, 6 plus x to the negative 3. And to make our formula work, we have to have this form, 1 plus quotation x to the k. So that 6 here is not convenient. We cannot make it work if we stick with a 6. We have to make sure it starts with a 1. Has to be 1. So here's what we can do. Let's factor a 6 out from underneath here. Like that, right? So they still have the same exponent of negative 3, but we took out a 6 from 6 plus x. And then we'll leave out the 6 to the minus 3 out here. And the important thing here is now we have the right form. Right? 1 plus quotation x to some exponent k. This is great. We can work with that. All right, so we're going to use the binomial series formula with k equal to negative 3, and our x is equal to x over 6. Once again, it's the top line here. That's the useful form to work with. Everything's going to get multiplied by 5 over 6 cubed. That's okay. That's just a constant multiple. It doesn't change what we do with the binomial series. All right? So here we go. First term is a 1. We're tackling this part now. 1 plus k quotation x. K is negative 3. My x is x over 6 plus k minus 1, k minus 1, 2 factorial, quotation x squared, right? And then k minus 1, k minus 2, 5, right? Over 3 factorial, quote x cubed, and let's go one more. Minus 3, minus 4, minus 5, minus 6, 4 factorial, x over 6 fourth, plus dot, dot, dot. Right? Okay, this time notice because k is a whole number. Now look at it. Look at the thing upstairs. Does it look kind of like some kind of factorial going on? Each one differs by 1, right? Now 4 times 3. I'm missing a 2 here, but it's almost looking like a 4 factorial. This is almost looking like a 5 factorial. This is almost looking like a 6 factorial. If I put a 2 in each one of here, each term here, I can get that kind of expression. So the numerators looks something kind of like a factorial kind of thing. And that's an indication that perhaps we should work with the factorials in the denominator to look for a way to simplify these things. So here's what we're going to do. These two, we don't have much to do with them, so we'll leave them alone. Upstairs on the third term here, this is positive. 4 times 3. Okay, that kind of resembles like a factorial. So let's spell out the factorial downstairs. 2 times 1. And then we have x squared over 6 squared. Next one, negative, 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 so overall negative. And let's do 3 times 4 times 5. 3 factorial. And same idea. Next one is positive. 3, 4, 5, 6. 4, 3, 2, 1. That's my 4 factorial. X to the 4th, 6 to the 4th, plus dot, dot, dot. Okay? All right, now, looks like even though I could reduce the 4 and 2 here, I'm going to leave them alone, and you'll see why. When I go to the next one here, I will take out the 3 here. And then over here, I'm going to take out the 3 and the 4. Right? So this is n equal to 0. This is n is equal to 1. N is equal to 2. N is equal to 3. And now we're looking for a pattern here. When n is equal to 2, my numerator has something that's 2 more than it and 1 more than it. Do you see that same pattern here? When n is 3, this is 2 more than that, 1 more than that. When n is 4, 2 more than 4, 1 more than 4. That shows up everywhere. That's n plus 2. That's n plus 1. N plus 1. N plus 2. Right? Every single one has the same predictable pattern in the numerator, including this and these. So let me further rewrite them a little bit. I'm going to rewrite 1 as 1 times 2 over 2 times x over 6 to the 0th power. And then this one, I'm going to write it as 2 times 3 over 2 x over 6 to the 1st. And then 4 times 3 over 2 x over 6 squared minus 4, 5 over 2 x over 6 cubed and 5, 6 2 downstairs x over 6 to the 4th plus dot, dot, dot. And once again, n equal to 0, n is equal to 1, 2, 3. The denominator of the coefficient is always 2 downstairs. Simple. But upstairs, it's always n plus 1, n plus 2. 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 Right? Every single numerator is n plus 1 times n plus 2. And because this time we could include 0 and 1 into the whole expression, the behavior fits. We'll include all of them. So a couple of things to remember here. We have alternating signs. We need our minus 1 to the n. Upstairs is n plus 1, n plus 2. Downstairs is a 2. And then 6 to the n. And then x to the n. Right? Let's bring our 6 into here. Let's bring the 5 in here too. Two, 6 to the n plus 3, x to the n. Right? So the difference between this and the last example. Last example, we couldn't get a very nice looking expression in here because k was not a whole number. It was a fraction. You cannot turn a fraction into some kind of factorial like you can do with whole numbers here. Every time when k is a whole number, an integer, we can do this kind of thing to further simplify. Questions? All right. All right, let's do one more, and then we'll call it a day. Oh, suppose we want to find the Maclaurin series of inverse sine. So we're going to have to differentiate or integrate something that ends up giving us an inverse sine. So we know that the derivative of inverse sine is 1 over radical 1 minus x squared. So notice that this is a binomial series here. And this is essentially the first example we did today in class with a different x, different k, but the same idea. So follow the first example we did earlier today, and you end up getting this kind of thing. See example 1. All right, so you end up getting this thing. Again, follow the first example we did to come up with that. And then notice the numerator is just a bunch of odd numbers, 1, 3, 5, 7, blah, blah, blah. And there, in general, all the odd numbers can be expressed as 2n minus 1. Right? Okay, now we know this thing here. If we want the inverse sign, because the derivative of inverse sign is this, to get inverse sign, we integrate it. We integrate that stuff right here. It's easier to deal with these term by term rather than the summation notation. This is a little bit complicated to deal with. And now we integrate that. That's not terribly hard. We get x minus x cubed over 3 times 2 plus x to the 5th over 5 times 2 squared, 2 factorial, minus x to the 7th over 7 times 2 cubed, 3 factorial, plus plus a constant, right? We integrated that to get a constant. I just dropped them. Oh, they're still there. They should be. There they are. Yeah. That's what happened to them. Thanks. Okay, now the pattern you see here, all the powers turned into odd powers. And downstairs is 2 to the... Let's do this again this way. And so on, right? And once again, you see the first one kind of looks nothing like the other ones. So we'll leave it out. And then the rest of them have alternating signs. We want to start with a negative, and n starts at 1. So minus 1 to the n works. Upstairs is our odd numbers, 1, 3, 5, and so on. 2n minus 1. And downstairs we have the same as the power of x first, right? And those are the odd numbers. When n is equal to 1, we want a 3. When n is equal to 2, we want a 5. When n is 3, we want 7. It's twice of n plus 1. And then we have 2 to the n, and then n factorial, and then x to the 2n plus 1. Yep. Plus my constant. To find a constant, one last thing, use the fact that inverse sign is equal to 0. So this should be a 0, and when you plug in 0 for x, you'll find out what this is equal to. Turns out that c is 0 too. All right, that's it, and that's all the series we're going to do. We're done with series until, well, we'll come back on the final exam. So we're done with series for now. Starting next week, we'll be doing something else. Okay, that's it. See you next time. What's that?
Sometimes